Good afternoon, everyone.
Hello, hello.
All right, let's get this started. Thank you, Mika. So yes, this is MaLDAPtive, diving deep into LDAP obfuscation, deobfuscation, and detection. My name is Daniel Bohannon. You can call me Debo for short. I'm a principal threat researcher at Permiso Security, a cloud and identity startup doing detection and response. I spent about 7 or 8 years doing endpoint research at Mandiant and Microsoft. I have an obsession. Some people call it a problem with obfuscation, but I've done a lot of projects in the past around this topic. And a more well-known problem of mine is I love coffee and books and all the great conversations that happen around those two things.
Hi, everyone. I'm Sabayeta. You can call me Sabi for short. I am originally from Albania and recently moved to Berlin to work for Solaris as a senior cybersecurity engineer. I'm mostly focused on cyber defense and doing a little of detection engineering and incident response, and when time allows, threat hunting. So I do have a little experience on consulting and governmental also. Love a nice mountain view, good movies, and a nice espresso.
All right, so to get started, we're going to talk about LDAP and Active Directory at a high level, and then we're going to dive in pretty quickly into some of the components that make up LDAP as a protocol. And then the majority of this talk is going to be on the fun stuff, on the obfuscation. And for all the other defenders in the room, the last part is for you, and we hope you really like it. So with that, we're going to start back in time to disco balls and DeLoreans. The 1980s, you have the Directory Access Protocol, or DAP. LDAP comes onto the scene in the 90s. It's the lightweight version of DAP. In 1998, OpenLDAP released OpenLDAP. And then for this presentation that's important to know, in 2000, Microsoft released Active Directory, which is the world's largest Active Directory service, which think of this as the server-side component that has all the information. And then LDAP is the protocol that client-side applications can issue to get that information out of that application. In the last decade, we've seen plenty of open source tools using Active Directory, issuing LDAP search requests, PowerView, BloodHound, PingCastle, et cetera. And these are really great for offensive and defensive purposes. So as defenders, we should ask, these tools are here, now what do we do about it? And this is kind of where it's a bit frustrating. Like, there are opportunities to get this telemetry in lab environments. We use Silk ETW from Ruben Boonen. But if you want it in a production environment, your choices are kind of limited. Microsoft Defender is the most well-known example for client-side and server-side visibility into those LDAP search requests. An important distinction here is there are differences between client and server-side. Client-side is an attacker's heaven. It's pretty much WYSIWYG. Any obfuscation you have that input into that filter and that query is going to look that way in the client-side logs. And a very important distinction here is that that is true if you're using a mechanism that uses WLDAP32.dll. So our friends over at Falcon Force discovered this and released something called SoapHound, which says, hey, let's do BloodHound stuff, but let's just do SOAP requests to bypass all these client-side logs. So there are those opportunities. So as defenders, it's important to also recognize server-side logs. There's a lot of normalization, some weird undocumented expansions, sometimes even producing technically invalid search filters, but both data sources are really important. So this is going to be a 40-minute maniacal speed run through all things LDAP search requests, parsing, obfuscation, deobfuscation, detection. We've spent over 2,000 hours of R&D on this, which is too much R&D to spend on one thing. We don't recommend it. And then at the end of this, we're going to demo and release MaLDAPtive, which is our open source framework for all things LDAP. The name comes from MaLAdaptive, which most people will think LDAP is pretty rigid and not that flexible, not that adaptive, and we hope to convince you otherwise very quickly in this talk. So with that, let's talk a little more about LDAP itself.
Let's dive into anatomy of an LDAP search request. So we're going to be looking at RFC 4511. There are different components to an LDAP search request, but we're going to focus on 4 main ones, which is the base object, where in the Active Directory we want to start the search, the scope that says how far to let the search run, the filter itself, which is what we want to get from the filter, from the query, and the attribute selection, which are the properties they want to get. So we've noticed that actually filter is mostly used by defenders, even for detection capabilities. For this reason, it's going to be our primary obfuscation focus, but we're not going to overlook also the base object and attribute selection, which are our secondary and tertiary obfuscation focus. Moving on to the filter itself, so since it's mostly used, let's see what it's made of. It's made of 5 required tokens, which is group start and group end. They hold in the middle the attribute and its value and the comparison operator. So there are two more operational tokens, which is Boolean operator and extensible match filter. Debo is going to talk more thoroughly about these in the upcoming slides. But just know that these are bitwise values that have different meanings based on the attribute. And Microsoft documents these very well. So in this case, for example, we are looking for an object which is not disabled. Most people actually don't want to do just a simple filters. They want to combine and bind multiple filters. And they do this by adding a Boolean operator, and we call it a filter list. So what is actually just like a simple row search filter? It is composed of two filters who together, they make a filter list. And then the whole string, actually, it is a search filter. Uh-oh. Sorry about that.
Sorry. No, we don't need help with PowerPoint transition. Sorry about that. Go ahead.
Moving on.
Yeah, okay. Looks like you could use some help with crowd work. Ha, hilarious. I don't know, trivia and jokes, what do you think? Should we go for it? Let's see, what do you call the biggest LDAP search request in history? 10.5 megs, because that is technically the maximum size. Now, Clippy comes with sources. Don't worry, he's not making things up. As defenders, I would encourage you to issue anything even remotely close to 10 megs and see just how much of it actually shows up in those data sources. Oh, man. Thanks, Clippy. Cool. So now that we've looked at kind of the LDAP tokens itself, let's now dissect them from an obfuscation perspective. For the defenders, it's going to get dark for a little bit. Hang in there. I promise you there's a light at the end of the tunnel. So as Sabi said, our main focus is going to be on the filter itself. We're going to enumerate a ton of obfuscation opportunities there, and then we're going to see which of those opportunities apply to the base object and the attribute selection as well. There are a lot of undocumented things that we found, so we will try to call attention to that. But if we forget, then just look for this little icon in the upper right. We're going to start by looking at these 5 tokens, beginning with the attribute.
So let's see what we can do to obfuscate a little the attribute. Well, we can do casing. Actually, it's case insensitive, so we can play with it a little. We can do object identifier notation. So the Microsoft defines this as a dotted string of numbers, which actually isn't quite true. We notice that if you actually add the OID.string at the beginning of it, it's still going to work, which is also case insensitive. So another thing that's really fascinating, and we noticed, is that it is also undocumented. If you add prefixes of zeros to each octet, it's actually going to execute just fine.
Oh man, that was undocumented.
Okay.
There we go. Let's go back just a couple. Clippy, come on.
So ANR, ambiguous name resolution. We can also do with ANR the same thing. So also the OID notation and insensitive casing. And it's also it's depending a little also on the Active Directory version. What is actually ANR? ANR is in case you know what you're looking for, but you don't actually know where it's residing. You can use ENR, and your search query is going to turn it into this query. So basically, it's going to add wildcards all over. And if you had, for example, in this case, we're searching for domain admins, and if you have a white space on your search query, actually, it's going to add these 4 queries too, because it will treat it as a first name, last name, first name. So some nice obfuscation tricks we saw. So we already know, for example, if we're looking for curb TGT, we can use ANR. The second option is, even the second option is going to work kind of the same way. So it's going to retrieve the same results, because in this case, it's an implicit wildcard. And the third undocumented thing that we found is if you actually put a wildcard after your search, everything after wildcard is going to be discarded. So you can play and add everything you want, and it's still going to have the same results. And these all 3 cases are actually covered in our detection framework. And if you don't care for the ANR and all the crazy stuff with the queries, you can just search with you can just add an equal sign, and it's actually the documented way to search in an LDAP query. So in review, to obfuscate the attribute, we can do casing, object identifier notation, and ambiguous name resolution. Cliffy again. Do you know where else ambiguous name resolution exists? I don't know, Cliffy, where? Microsoft. What is more ambiguous than resolving to rename your products every 6 months?
Oh. I didn't know Clippy was allowed to make Microsoft burns, but OK. Thanks, Savi. So one token type down. We've talked about attributes. Let's keep going. The second one is the comparison operator. Most of the time, this is an equal sign. But LDAP in Active Directory does allow you to have an approximately equal to. Case still doesn't matter, but things like wildcards and hex, which we'll talk about in a little bit, aren't working. We're going to focus pretty heavily on these two range comparison operators. And let's take a specific example. Let's say that you wanted to do a logical equivalent of a presence filter. This is a presence filter, a precursor of Kerber roasting, saying, give me the objects that have a service principal name property that is defined to be any value. I don't care what. Well, technically, we could change that to be greater than equal to a string starting with the equal sign, or starting with the exclamation point, or less than ZZZ. Again, this is doing the same thing, saying, give me objects with this property with a name that evaluates to the logic that's here. One really, really bizarre thing that we found is, so this is what the correct order, the standard order of characters in the printable ASCII range. We found that strings in Active Directory LDAP just don't give a crap about this. So they don't care about casing. You have digits and alpha at the end. You have this weird grouping of these special characters as bookends, and then all the other special characters fall in between. This is the ordering in Active Directory LDAP. We don't know why. This is a real frustrating bug to find, but our tool basically handles that, so if you're adding in any particular ranges, it takes that into account. Another thing we can do is logically equivalent range filters. So this is an example of a bitwise attribute. And let's say we wanted to write this, but detections were looking for this. So instead of saying the number ending with 368, we could say the number ending greater than equal to 7, less than equal to 9, and those things together. And then let's also explicitly exclude 7 and 9. So logically, this gives you the exact same value. Now, if you're a more visual person like me, I think about this as a timeline. Greater than equal to 7, less than equal to 9. And then our specific exclusions to get us right down to 8. In the obfuscation module we built for this, we have a couple of different recipes. One of my favorite ones is doing exclusions of ranges. My really favorite one is doing 2 opposing exclusions. So start with a search with a presence filter, and then exclude both directions out. And all 4 of these are going to give you the exact same logical equivalent for that number. You can also do this with strings, but keep in mind the suffixes become a little tricky to deal with, so we kind of consider this like a lossy obfuscation function, but it's still quite a great way to get around a lot of detections. So in review for that second token type, we have approximately equal to, but a lot of the fun comes with those range filters for presence and range filters. Those last 2 examples should look pretty familiar to you. They're actually found in BloodHound in their SPN target enumeration. So for those of you who are defenders in the room, these are actually really relevant examples of how you can basically get that logical equivalence in a way that would likely evade a lot of detections, expecting it to look something like this. The third token type is the Boolean operator. Most of the times, we just think of this as ands and ors. The not is what really spices things up in LDAP. So let's take an example. Let's say that you're looking for countries equal Albania. This is the object you're looking for. Well, one thing you can do is just throw in a bunch of group start, group ends, and a lot of and or, and it's still going to evaluate to the same thing. You can also add double negation. So notting a not is the same as nothing at all, and so this is still going to evaluate correctly. Another kind of note here is you can actually place Boolean operators directly inside the filter itself. Microsoft acknowledges this and says it's not really recommended. And actually, if you look at the server-side logs, the server will insert additional parentheses to kind of make it correct. But on the input, this is totally valid. And these are all scenarios that we built into our parser to basically handle so that we can know the difference between these. So let's take a little more interesting example. Country equals Albania and either of these 2 other things. Location equals Kukës or Tirana, which are 2 cities in Albania. So the important thing to note here is each Boolean operator has kind of like what we're going to call a sphere or a box of influence. So these are these 2 colored boxes that we see up here. And actually, if we make it even a little more complicated, we have 3 boxes. So when we're parsing this, we have to track all these Boolean operators and assign the group, which is basically a stack, to say these are the orderings of bools that apply to each filter. This is really important to know, is this logically anded or ored when you have 2, 3, 4, 20, 30, 40 Boolean operators affecting one filter. And if you have a not Boolean operator, nots are different. They don't affect everything inside of that filter list. They only affect the first Boolean operator or filter they come into contact with. So you can see this not is affecting location equals cookies, but does not affect name equals hobby or anything else past that. And again, we track all this. There's some really interesting features of the not that are really frustrating to deal with, but put it in the parser so we didn't have to think about it going forward. Logical inversion is probably the coolest thing you can do with Boolean operators. For any math nerds in here, this is called De Morgan's law. So not A or B is the same as not A and not B, and the inverse is also true. So we can apply this to any LDAP filter by choosing a spot to put a not. In this case, we'll select the whole filter. That's step number 1. Then everything else wrapped inside of that is now in scope. So step number 2 says let's find all the ands or ors and invert them. Ands become ors become ands. And lastly, let's find all the filters and invert those from a negation perspective. So none of these are negated, so we're going to add the not Boolean operator. If not was present, we would have to remove that. This is logically equivalent to what we started with. And again, this makes it really complicated when you're trying to figure out in a parsed entry if something is actually being included or excluded. So in review for Boolean operators, we have the additive nature, double negation, and De Morgan's laws for the logical inversion. All right. What is my least favorite LDAP token type? I'm guessing Boolean operator since we're already here. Yep, because I'm afraid of getting tied up in knots. That was cringe, Clippy. Oof. We started high and we were going down very fast. So let's get that out. Yeah, get that off the slide. All right, the fourth token type is the extensible match filter. We talked about this example earlier. This is how you can have and or logic for bitwise values. Active Directory LDAP supports 4 different values. Ands and ors are first, and then later versions have these other ones. We're going to focus exclusively on the ands and ors from an obfuscation perspective. So for example, if you had this filter, you are anding these bitwise flags to come up to the value 515. What you can actually do is break those out into smaller subgroupings. As long as you're dealing with base 2 add-in values, then 1 and 514 anded together is the same as 515. You could break it out even further. Now you have 1, 2, and 512. And if the starting point was an extensible match filter for or, that's fine. It works just the same. You just make sure you're bringing in an or Boolean operator instead of an and. Another thing, this can actually get pretty complicated in real life. Here's an example from Get Domain User from PowerView, where it has a quite large number. And so think of all the random groupings you could do to break this logic out into multiple filters. So in the obfuscation module we built, this is exactly what we did. And it definitely complicates detections because you're now moving all that logic across multiple filters throughout the entire search filter. Another thing we can do is we can take a precise filter like this. This says, give me the object that has precisely this value, these exact 1s and 0s in the bitwise flags. And we can convert this by using this formula into a broken out version. So we can and all the 1 bits, we can not or all the 0 bits, and then we can and those things together. So this is logically the same as what we started with for that precise value. But if you'll notice, now we have filters that have extensible match filters. So we can go back to the first bitwise breakout and break these out even further. So again, we're really moving the logic into a lot of places to make it quite tricky from a detection perspective. So in conclusion, bitwise breakout and bitwise breakout of precise values are some of the methods that we can use to obfuscate these values that have bitwise. And the parser handles all this for you, as we'll see in the demo towards the end.
Thanks, Ivo. So moving on to the filter for the value itself, let's see what we can do obfuscating. We can still do the casing, as in previous examples, exclude some attributes with value formats. And yeah. So we can also do prepended zeros on all the values that it's bitwise digits or numbers. We also got some undocumented feature timestamps. We noticed that sometimes milliseconds were present, but it didn't seem to matter. If you change the milliseconds values or remove them, it turns out that you can add literally anything you want as long as you add a capital Z in there. So still, this one is going to be a timestamp. Fun fact is actually you don't even need to use just the upper Z case. You can also write the hex representation of it, and it's going to work. So, which leads us to our next point, which is hex encoding. This is our favorite thing to do, obfuscation-wise. So it exists, the hex encoding itself, it actually exists to escape certain special characters, which Microsoft has detailed here. But you can also escape any printable characters that you want as well. So you can swap these with their hex representation, and it's still going to work and return the same result. Our parser parses, codes, and decodes all the values on the hex representation of it, so you don't need to. Another thing undocumented is that Microsoft said that the hex representation should be followed by 2 characters representative of their ASCII character, but that's actually not true. We discovered that for the first 16 characters, you can actually drop the leading 0, and it's still going to work. Wildcards. So we also saw a little the wildcards. For example, instead of looking for curved TGT, you can also look for just RBG here, and you're going to get still the same results. Obfuscation for the evasion purposes, actually, we're not the only ones that we're looking at the wildcards. Hope Walker, a researcher from SpecterOps, also has detailed in these 2 articles how, and outlined how using wildcards for evasion purposes. A quick review for value obfuscation, we have casing, prepended zeros, timestamps, hex encoding, and wildcards. The good news is that's all you can do with obfuscation. Nah, I'm kidding you guys. We got a lot more. So until now, we actually saw only the tokens. Let's see what we can do outside of it. So filter-wide obfuscation. You can actually add group start and group end as much as you want, as long as you keep a depth of 99. White space, you can also add it and remove it all over. New line, be it tab, whatever. So garbage filters, also in this case, you just need to be careful if you're using logical or logical AND, because if you're using logical AND, actually you need to make sure that the attribute exists. But with OR, you can actually go crazy and just add whatever you want. Filter and filter list reordering also. So as a recap, until now, we've seen the filter. Let's see for the base object itself. Quick reminder, the base object is where in the directory structure we want to start our search. So we've seen that there are some good detection opportunities that we feel are not as much discussed. For example, this tool, offensive tool, Certify index example, actually uses a super common search filter. So the base object, in this case, is very specific. So it's looking for public key services. And we are going to be focusing on the syntax perspective, how we can obfuscate a little, a simple base object like this. The same trick as we already discussed, so we can do casing for the value portion. You can also do hex encoding for the value portion of the relative distinguishing name, or object identifier notation for the attributes. Also supports the added dot prefix and the prepended zeros. And white space can be added at the end, as well as in between the slashes of LDAP prefix. Something is interesting that is true only for the base object, but not for the value itself, is that as long as the hex is not present, then you can actually encapsulate it with a double quotes, and it shows this way also on client-side logs. But it's not going to look like this on server-side logs. Lastly, the attribute selection, which is basically which attribute properties do we want to be returned in our search results. And for attributes selection, we also have casing. We have the object identifier notation, and it also supports OID prefix and prepended zeros. We can add white space only after attributes that are on the OID syntax. Not sure why, but yeah, we learned after some trial and error, a lot of it. And we have also the option to add double attributes or garbage attributes. You can literally add whatever you want. And the person who is going to answer for this is no one else than Clippy. What do you call this character, Daniel? Asterisk, wildcard, or split?
Well, I think older people in the room would have different answers than me, perhaps, but I'm guessing with all that space down there, Clippy has some extra Yeah, so all of the above, including 2 more answers. From an input perspective for attribute selection, if the only thing you define is a wildcard, then it will return all the properties, but it's actually the same as if you don't define attribute selection at all. They're logged slightly differently. In server-side logs, that asterisk will be logged as square bracket, the word all, lowercase. Now, the really interesting scenario is if you define many attributes like Sabi was showing, and one of those attributes is a wildcard, or at least one wildcard is present, then what it will do is it will actually turn that wildcard into this string all with list, but weirdly, it actually prepends it to the very first attribute in that delimited list. So if you are parsing attributes, which you should be, then definitely keep that in mind and make sure you break that out. Otherwise, the first attribute is going to be joined with this one. From a defensive perspective, a lot of people don't really think about attribute selection. They're logged exactly how they're put in. So the ordering is very precise. So a lot of people don't change their tools to, anyways, I don't need to go into that. But yeah, there's options there. So that's actually the end of the obfuscation portion that we're going to be discussing. So now for all the defenders in the room, let's talk about where do we go from here. And we're kind of going to outline it in 3 pieces, which is parsing, enriching, and detecting. So parsing, when we started this research, there wasn't a parser for LDAP search filters that we could find. So we built one, and that was, no joke, probably half this research was building a parser. The hardest but most fun thing we've ever done, we built a state machine parser in C# for performance. The rest of the project is a PowerShell wrapper to have all the cool pipeline ability and flexibility and randomization that PowerShell is really good at in obfuscation frameworks. So think of parsing as this. First, we needed to have a tokenizer, which says take all the input string, just this massive string of an LDAP search filter, and break it up into little tokens. Here's an attribute, here's a value, blah, blah, blah. Next, we want to organize those tokens into something that has a little more meaning. And so we chose to do it as a syntax tree or a parse tree. This is not an abstract syntax tree. It's on the journey there, but abstract drops things. It is abstract, so it drops things that it considers insignificant, but we still consider significant. So step number 2 is enriching. So you can see here actually using the tool to parse from a string to the tokens. All along the way, we are also adding additional decoding. So whatever hex characters are present, we decode that for you. Or bitwise characters are present, then we enumerate those flags. And then we group those things into filters and branches and trees for different kinds of obfuscation and deobfuscation techniques. And lastly is detecting. This is the whole reason that we did this research in the first place, was how can we detect all this stuff that we are kind of discovering or inventing or putting together. So find evil is the function we created that does all this. Give it any search filters you want, and it will parse, enrich, detect, and all those detections carry with it scores, explanations, even pulling out specific values from the search filter that flagged on that rule. We want to give a really big shout out and thank you to Olaf Hartong over at Falcon Force. He was so kind to basically take all of our rules for us many times and run them against his client data set and provide us kind of stats of which rules sucked and needed to be tuned a little bit. But so thank you, Olaf, for that. Definitely helped us tremendously in the rule set that we are releasing as part of this research. And lastly, if you look at the bottom, because we spent so much time on this parser, we did it to make it as blazing fast as we possibly could. We wrote and rewrote probably everything in this parser 2 or 3 times, just for our own learning experience. So here's an example of us parsing this search filter 100,000 times, running it against all of our 65 and counting rules, clocking in at just under 4.4 seconds very, very consistently. So with that, instead of talking more about the solution, let's just show people. If you haven't picked up by now, we really like to have fun. And so in this tool, we put as many colors as we could think of, but there actually is a method to the madness. It is there to help quickly figure out what part of a search filter is attribute, value, all that kind of stuff. This is the ASCII art for the tool. This is a valid LDAP query. It will return anything with a name. And there's a couple Easter eggs in there if you have time for it. So the first example is going to be taking a pretty simple search filter. This is that Albania Kukas Tirana example, and we added some hex encoding and some OID syntax. So we can see we can tokenize it, and we can say, hey, which pieces are an attribute versus a value. That enriched token is now going to say, hey, here's an attribute, and it's defined. And it actually resolves to this attribute name, and we have these context objects. Context objects have all the great things with like Boolean operators we'll see in a moment. We can group all these things together into LDAP filters, so we can evaluate logic on the whole filter. We have immediate access to all the tokens in that filter, the values, as well as the full token dictionary and token list. So any way you need to access that data, you have all that at your fingertips. Now, if we look at the context object, we can see all the Boolean operator. This is that stacking of Boolean operators as we parse to say, hey, this is logically inclusive, this is an and or an or, and we have full access to all the tokens of the Booleans. And then for every value, we do full parsing. So we parse the hex. If we run it through the find evil function, we can see all these rules that flagged on different components in this search filter. The next example is going to be looking at a bitwise value. So in this case, this is our search filter. That middle one's going to be a little interesting. If we pipe this into find evil, it matches on a very specific rule that we wrote, looking for the user account control attribute with a flag of 128 set. And as we're going to show you in the parsing of this filter, in the value, we automatically figure out it was a bitwise value based on the attribute, and then we parsed all the zeros and ones, both in a dictionary format as well as in a list format. So whatever format makes sense for you, you can go and then write detections very specifically against those without needing to care about what the actual integer number is. You can go right to the flags and get to the source of truth. The last example is having fun with some of the wildcards. So hex decoding, that's easy sauce. Like, we already do that out of the gate. So trust the domain for that first example. That's simple. What about all these wildcards? You're actually dropping characters out. So in our detection module, we have the ability to define high-value strings as values, and then the parser will go through, and it will basically expand those wildcards and say, hey, does this match against any of these high sensitive values? This also handles the two ANR scenarios that Sabi mentioned of the implied wildcard and the explicit wildcard. So again, we try to think of as much of this as we could and bake it right into the detection framework so it's as easy to use right out of the gate for all these techniques.
And finally, we've put all this together into a colorful interactive menu to make it fun to explore. We can test our input, the LDAP search filter, and we can explore the obfuscation menus for all the techniques we covered in this presentation. Wildcards are also supported. We can add obfuscation layer by layer, also remove it. And if you're lazy, you can also use all wildcards to randomly apply all the options. Testing again, the filter, the search filter will show that it still works. And the detection module is built in, and find evil shows a full summary of detections, scores, explanations, and more colors, of course. Lastly, if you don't like the interactive menus, we have full CLI support. So the interactive menu lets you randomly choose ingredients, and you can copy the recipe for a non-interactive user. All the patterns are for printing, and detection summaries are also available via CLI.
All right. Now, before I go to this next slide, I would just like to remind everyone that Sabi and I are both defenders, always have been, and that was our initial intention of this research. So the next slide was our own volition. No one strong-armed us. Today, we're releasing everything you saw except the obfuscation module. That was our decision because attackers don't really need this machine gun right now. Defenders need ammunition. We just talked about how many people don't even have visibility into this data source to begin with. So we made this very clear in our CFP submission. 4 bullet points, red text. We want to release everything except for this thing. And our goal is by the end of this year, pending CFP acceptance or rejection, our goal is to release the obfuscation module by the end of this year. It's done. It's been done for months. It's what we use to develop all the detections. And it really, people ask us, why do you do obfuscation stuff? It's so freaking weird. Well, it actually is a way of like orchestrating chaos. So you know where the boundaries of things are so that you can write those detections. And writing the obfuscation module literally taught us undocumented things about LDAP. So that's why we do it, because otherwise we would have written half of these detections and thought we were done. But this really helps us kind of maximize that energy and those efforts. So right before this talk, we pushed, the last slide will have the GitHub URL. This code is live, and again, it's the entire parser framework. It is the deobfuscation modules, the detection modules with the complete detection rule set, and it also is an obfuscation corpus. So we have 1,337 obfuscated examples of benign search filters that you can use to test your detections or to test our detections and see just how it works. So with that being said, our 3 main takeaways. LDAP still being used by attackers, and search request is the mechanism in which we can kind of see what they are querying out of Active Directory. Defensive awareness and like from a visibility perspective, even just from a detection perspective, we feel like it's just still kind of immature. And so we hope that this research will bring light to that. And we really hope that a net benefit of this is more people will find creative ways of getting that telemetry in their organizations. We love to see more options to get this telemetry, but that's our second point. And lastly, we released MaLDAPtive as an open source tool to hopefully make all this easy so you don't have to spend nearly as much time as we did looking at all this stuff. We have one more thing we'd like to show. This is our unofficial takeaway. We've had a lot of fun working on this together, and so we wanted to leave you with our 2 favorite Albanian proverbs. I'm not a native speaker, so forgive my pronunciation. My favorite one is Rofsh sa malet. And literally this translates to live long like a mountain. And it's kind of a greeting or a blessing of prosperity and well-being. And so I feel like together we all climbed a pretty big mountain, so I'm a little winded from it. But what I want you to take away from this is help other people up that mountain. Show them the path that you took so they can get to the other side and see the next peak to go climb. As a security community, we really have to be there for each other to build on the shoulders of those that went before us and to not use it to beat someone over the head with a stick, but to really help all of us make progress together.
And my favorite one, and I think the audience will also agree, is to lutem iomocapse letrash, which it means, please no more paper clips, Daniel.
I won't say whose idea the paper clips were, but okay, okay. Very authentic Albanian proverb. So with that, thank you all so much. We had so much fun doing this research. This has been a blast to come together and present this. We've really been thinking about this for too long. I'm really happy to get it out there today. And with that, here's our contact information. Here's the link to the code. And thank you all so much for your time. Any brave souls for questions? Otherwise, we'll be in the overflow room for less brave souls that want to ask questions. But any questions so far? Yes, right here in the middle. Thank you.
Maybe one question. You said detect, not just in the aftermath, but how do you want to use the tool as an active detection to see that somebody is actually doing it right now? Like, what would the setup look like?
Yeah, that's a great question. So the way in which we would actively use this would be whatever data source you have of your LDAP search filters, distincting those and then piping them into this find evil function and consuming those results. So at least tell you, hey, these are the search filters that have a high score. Now, in the grand scheme of things, if you have something like Defender telemetry, there's a lot more than just the search filter. You know, Sabi explained the base object, the attribute selection, even the process making that network connection. Now, you don't have the process element in server-side logs. That's why we focused everything just on the search filter in isolation, because that server, that's all it's going to give us. But yeah, all those things together are really, really important. Did that sort of answer the question?
Yeah.
Awesome.
I have a second question.
Yeah.
You talked about obfuscation techniques, for example, adding leading zeros or adding the set in a timestamp, which sounds really funny. Isn't that already like a key giveaway for you as a defender? That's if somebody uses leading zeros, or is that also that could naturally happen in that environment?
Yeah. We've seen naturally occurring single zeros leading values, like bitwise values, integers, but no, for the OIDs, we do not know of that occurring in the wild anywhere. So it's a great question. Like, obfuscation, like when you look at these examples, they look pretty unhealthy. Like, that is kind of the point. But if there are millions and millions and millions of these things flying around, if a human eyeball doesn't see it, then there's never the opportunity to ascertain that it is unhealthy. So that's why I think, so I'm not a red teamer. I'd love the inside of red teamers in here, but like, I'm sure there's a trade-off. Like, if you know you're going to get up against some really good defenses, then maybe a very specially crafted, what I'd call like tastefully obfuscated example might be enough just to bypass. Honestly, just instead of saying service principal name equals wildcard, using the OID might be enough. The OID of the attribute mixed with greater than equal to equal. Like, that might be enough to get around it. So, so yeah, I assume the objective for a red teamer is don't draw attention to this enough for eyeballs to look at it, because if you got there, then you're burned.
Yeah. Thanks a lot.
Yeah, great questions. Thank you. Yes, right over here.
Do you reckon it would be possible to create a KQL query with the LDAP search event that would kind of score whether something was obfuscated in an LDAP search that might indicate malicious activity?
There are certainly some things that you could do. I mean, so we built the parser to get to crazy depths of stuff like counts of Boolean operators in scope. We have this concept of scope application versus scope syntax. There's a lot of weird stuff that probably no one will ever get to unless they built this tool. So like, what I would say, so first of all, KQL, freaking awesome language. So there's a lot that you can do there. For example, if you have Defender telemetry, I'm assuming maybe that's the reason you're asking the question. There's a lot you can do with KQL for like the attribute selection and the base object stuff. Should base objects, as Sabi was talking about, hex encoding, should you ever have hex in base objects? Should you ever have more than 2 adjacent white spaces? Probably not. That's a very simple query, whether you're using KQL or Splunk or anything else. Attribute selection as well. Like, do you ever see dots anywhere in attributes? That's a dead giveaway for you're dealing with an OID notation. Do you ever see leading white space after one of those? Like, so there's a lot that you can do there with those 2 elements. And there's a lot you can do with a search filter, but just know that there's use whatever tools you have at your disposal. There's some deeper insights we try to glean out with the parser, but definitely using KQL straight against it would be a great approach. And we hope people will go and do that. So.
Okay, so if I get it right, you haven't really looked at big data sets to see what kind of obfuscation happens in benign situations?
We have never seen obfuscation in large data sets. We do not have access to large data sets directly. We have friends who have run these things in large data sets and have not found anything.
All right, thank you.
Thank you, great question. We have 20 seconds, so I assume that means we're done with the questions. Thank you again, everyone, so much. We really had a lot of fun. We'll be down here at the front afterwards. Thanks, y'all.